Okay, picking up where we left off, we had just gone over a couple of molecular equations for acids and bases for hydrochloric acid and sodium hydroxide and hydrochloric acid and magnesium hydroxide. And what I wanted to do now is just show doing the molecular ionic and non-ionic equations for those two reactions. The molecular equation is essentially what we wrote up here. And the ionic and non-ionic equation we can take from that. If the reactants are strong acids and strong bases, then that means that they will ionize completely in water. And so HCl will actually be present as H plus and Cl minus, both aqueous, but I've gotten lazy and decided not to write that. Plus, the NaOH will be present as Na plus OH minus. Again, both aqueous, but I decided not to write it. The products NaCl will actually be present as Na plus and Cl minus. But remember, H2O, while being soluble in water, obviously, is not an ionic compound, so it will not ionize. And so it will be present as H2O liquid. And now you can go through and look for spectator ions. And we find that H plus comes out as part of water, so that needs to stay. But Cl minus comes out exactly the same as it went in, as Cl minus ions, so that can be canceled because it's a spectator ion. Na plus ions, as I said, are always spectator ions, and sure enough, there they are again, exactly the same as they went in, so we can cancel those. On the other hand, the OH minus is part of H2O, so when it comes out, so that has to stay. So our net ionic reaction is H plus OH minus yields H2O. Just what I said it would be, because that's always the non-ionic equation for strong acid and strong base type reactions. You can look at the other, we can look at another example, say sulfuric acid plus sodium hydroxide. And when we balance that, we find we get sodium sulfate, so sodium sulfate, and hydrogen hydroxide, better known as H2O or water. And we can go through the entire process for finding the ions. The H2SO4 is a strong acid, so it will be present in water as 2 H plus ions and 1 SO4 minus 2 ion. And the sodium hydroxides, if there are 2 sodium hydroxides, then that's 2 Na plus and 2 OH minus. All of these ions would be aqueous, of course. And for the products, Na2SO4, like most sulfate compounds, is soluble in water because it's a sodium compound. They're all soluble in water. And so we'd have 2 Na plus SO4 minus 2 plus 2 H2Os. And then you go through and you cancel out the spectator ions, and we get 2H plus 2OH minus yields 2 H2Os as the net ionic equation. But we would want to divide that by 2 because all the coefficients are 2. So when you divide by 2 to get the lowest whole number ratio of the coefficients, you get H plus OH minus yields H2O, just like we did up above. And that's because, like I said, that's basically always the net ionic equation for any combination of strong acid and strong base. And there is an exception, but don't worry about that. I won't put that on any tests or anything. That's an overview of acid-base reactions. If we get that far in the text, there will be a lot more detail coming later. But for right now, we want to move on and have an overview of oxidation-reduction reactions. These are sometimes called redox reactions, and it kind of combines the words oxidation reduction into one word that's much easier to say. And it's safe to do that because oxidation and reduction reactions always occur together. So that's one thing to remember. If you're talking about oxidation, there's got to be a reduction going on somewhere. If you're talking about a reduction, there's got to be an oxidation going on at the same time. You'll never have one without the other. Some reactions we refer to as one or the other because of, say, an aspect of the reaction that we care more about. So like when your car rusts, we often refer to that as an oxidation because it's the metal that's oxidizing into iron oxide, which is rust, and it's the metal that you're going to have to go to the body shop and pay big bucks to get repaired. At the same time, though, oxygen from the air is being reduced. We don't really care about that, though, because there's plenty more oxygen where that came from. We don't have to pay for it. And, so we call it an oxidation. But there really is a reduction going on also at the same time. And so oxidation reduction reactions are reactions that involve transfer of electrons from one reactant to another. So it's kind of, not exactly, but kind of like forming an ionic bond, where, an ionization, an electron goes from the metal to the nonmetal. In this case, it's not always metals and nonmetals that are involved, but and the transfer is not always complete, but there's usually at least a partial transfer of electrons from one thing to another. And in practice, it's often easiest to recognize as a reaction with or a loss of oxygen or hydrogen. So there are essentially three definitions of oxidation and reduction. And as I said, they both always occur together. And now that we've seen one of the definitions anyway, it's easier to see why. Because if it's a transfer of electrons from one place to another, then one process would occur in one place and the opposite process would occur in the other place. Because that electron has to go somewhere. It can't just disappear. And electrons cannot just exist on their own for any length of time. So if, say, an electron is lost by one reactant, that's an oxidation, as we'll see in a moment. It has to go somewhere. Something else has to take that electron in, and that's a reduction. And so that's why they always occur together. So the definitions for oxidation and reduction, I put them next to each other because they're essentially the opposite of each other. There's a definition that involves oxygen, one that involves hydrogen, and one that involves electrons. I've underlined the electrons because that's kind of the most universal definition, although the oxygen and hydrogen ones are often easier to spot when you see them. So oxidation would be a gain of oxygen, and reduction would be a loss of oxygen. For hydrogen, though, oxidation would be the opposite. Oxidation would be a loss of hydrogen, while reduction would be a gain of hydrogen. And in terms of electrons, an oxidation would be a loss of electrons, and a reduction would be a gain of electrons. And this is easy to remember by the little device Leo says grr, like Leo the lion says grr. Loss of electrons, oxidation, gain of electrons, reduction. So that the electron definition is probably the most useful ultimately, and also the easiest to remember because of that. A simple example of oxidation reduction reactions would be, first of all, any reaction that involves a free element, either as a reactant or a product or both, will definitely be oxidation reduction. And a simple example would be combining sodium metal with chlorine gas as the free elements. When you put them together, they will react spontaneously with a bit of a boom to form sodium chloride solid. And to balance it out, it needs to be two sodiums because chlorine only comes in pairs, and that would give you two NaCl solids. As it turns out, you can break any oxidation reduction reaction down into half reactions and look at just the oxidation and just the reduction separately. And that's what we've done here. These are half reactions. We look at the sodium, for which there are two of them, and that has zero charge because it's the free element. So I wrote a little zero in to emphasize that. And what happens is each sodium gives up one electron. So each sodium becomes Na plus and gives up an electron, but there are two sodiums, so that's a total of 2 electrons. So sodium loses electrons to become Na plus, That's an oxidation. What happens to the chlorine, though, is that each chlorine gains an electron, and so it's 2 plus 2E minus as a reactant, to form 2 chloride ions. And these are the same 2 electrons. The 2 electrons taken in by the chlorine atoms are the 2 electrons released or produced by the sodium atoms. So when you see something on a product side, that's kind of the same as losing. We say that sodium lost 2 electrons because, in effect, sodium produced or gave off 2 electrons. And then the chlorine takes them in. So each chlorine atom gains 1 electron to form Cl- ion, and that's a reduction. So you've got oxidation, reduction. And in practice, when you add together the oxidation and reduction half reactions, you get the overall reaction. Because look what happens when you take 2Na with no charge plus Cl2 with no charge plus 2 electrons. So we're basically dividing these 2 half reactions at the arrow and adding up everything before the arrow and everything after the arrow. And look what happens when you cross out things that remain the same on both sides. Na0 with no charge comes out as Na plus. So that's a change. You can't cross that out. Cl2 with no charge comes out as 2Cl minus with a charge. That's a change. Can't cross it out. But 2 electrons come out as 2 electrons. That's no change. So you can cancel those out when you're combining the half reactions. And what you get is our overall reaction. And of course, 2Na plus 2Cl minus is equivalent to 2NaCl. And that was the overall reaction that we started with, this leading to this. Okay, so one easy way to remember oxidation from reduction is that in oxidation, the oxidation state, that is the charge on the substance that's being oxidized, goes up. So when we're dealing with oxidation reductions, the charges on the various reactants and products are referred to as oxidation states or oxidation numbers. But you can think of it as just the charge. For the oxidation, the thing that's being oxidized, the charge goes up. Well, sodium went from 0 to +1. That's an increase, so it's being oxidized. Reduction is even easier to remember because reduction is a reduction in the charge of whatever's being reduced. So the oxidation state or the charge goes down. Chlorine starts out with the 0 charge and ends up with -1. That's a reduction. So it's a reduction, literally. Now, a more challenging concept is the idea of oxidizing and reducing agents. Since both of these processes occur at the same time, and since it's the same electrons that are being released by the reactant that's being oxidized and taken in by the reactant that's being reduced, you can look at it as the substance that's being oxidized is causing the other substance to be reduced by releasing electrons that the other substance can then take in, thus causing it to be reduced. So the substance that's being oxidized can be termed the reducing agent because it causes the other thing to be reduced. Also, looking at it the other way around, the substance that's being reduced is taking in electrons from something else. And when the substance being reduced takes in those electrons, it's reduced. But by taking those electrons away from something else, it causes the other substance to be oxidized. And hence the substance that's reduced is the oxidizing agent, causes the other stuff to be oxidized. And so up here, notice that sodium is releasing electrons. When it does that, sodium is oxidized, but those electrons are then taken in by the chlorine, in which case the chlorine is reduced. So the sodium, by giving up electrons, causes the chlorine to be reduced. Oops. Sodium gives up electrons, which are then taken in by the chlorine. So the sodium is oxidized, but it causes the chlorine to be reduced. So the sodium is the stuff that's oxidized, but it's also the reducing agent. It causes something else to be reduced. The chlorine takes in those 2 electrons from the sodium, and the fact is the sodium is not going to release those electrons until there's something else nearby that's willing to take them in, like the chlorine. So by taking in those electrons from sodium, the chlorine is reduced, but it allows the sodium to be oxidized. And so the chlorine is reduced, but it's the oxidizing agent because it causes oxidation in something else. The easiest way to remember it is just that the word agent turns it around. So the reducing agent is the stuff that's oxidized, and the oxidizing agent is the stuff that's reduced. Okay, so that's what I'm concluding down here. Okay, due to the other definitions, you can actually have redox reactions in which an electron or electrons are not transferred fully. You can think of it as kind of a partial transfer of electrons. So you start out maybe with a situation in which the electrons are being shared equally by 2 identical atoms, and you end up with a situation in which the electrons are being shared unequally in a bond between 2 different elements, and one of the elements wants electrons more, but they don't have the ability to actually take the electrons away from the other atom. So for instance, if you take hydrogen gas and chlorine gas and combine them, you will get hydrogen chloride gas. And that wasn't balanced, so now it is. Okay, that's better. In hydrogen gas, you've got 2 hydrogen atoms bonded together, and because those 2 hydrogen atoms are the same as each other, they each have the same level of attraction for electrons. And so the electrons are shared equally between the 2 hydrogen atoms. The same is true of the Cl2. That's made up of 2 chlorine atoms, and the chlorine atoms are the same as each other. They have the same level of attraction for electrons, and so the electrons within that molecule are equally shared between the 2 chlorine atoms. But our product is going to be 2 molecules of HCl. And that compound, the Cl, has a much stronger attraction for electrons than the H does. And so the Cl draws the electrons closer to itself and away from the H. And the result is an unequal sharing of electrons. And that's what we can think of as a partial transfer of electrons. The same kind of thing happens when combining hydrogen and oxygen to form water. In hydrogen, again, equal sharing between the 2 hydrogen atoms. In oxygen, it's O bonded to O. So the 2 atoms are the same and they share electrons equally. But then when you combine them into H2O, you have 2 molecules that look like this. And the oxygen, as it turns out, has a much stronger attraction for electrons than the hydrogen does. Not strong enough for the oxygen to rip the electrons totally away from the hydrogen, but it is an unequal sharing. And so that will be essentially a partial transfer of electrons from hydrogen to oxygen. So it still counts as an oxidation-reduction reaction. It's just that it's not a full transfer of electrons, or in other words, it's not a full ionization. because a full transfer of electrons is ionization. Sodium becomes Na plus, chlorine becomes Cl minus, and because they have opposite charges, they're attracted to each other, and that's an ionic bond. These electrons were transferred fully from the sodium to the chlorine. In this case, we've got entirely nonmetals, and so even though one of the elements may have a stronger attraction for electrons, it's not strong enough to completely take the electrons away from the other atom. So they're still shared because the products are covalently bonded, but it's shared unequally, and that's what we mean by a partial transfer. Now, in discussing that a moment ago, I mentioned oxidation states or oxidation numbers, and it's basically the idea is the charge that's on an atom in a given situation. That's what the oxidation state is. In cases where you have ionic compounds like sodium chloride, the oxidation state of an ion is just the charge on the ion. And so that's really easy. But in situations like we just saw at the bottom of the last page, where you're forming covalently bonded compounds and you don't have a total complete transfer of electrons from one thing to another, you don't end up with full charges on the atoms in the compound. You end up with partial positive or partial negative charges, like for instance in water. Water has a stronger attraction for electrons, so it will pull electrons in from the hydrogen, and you'll end up with a partial negative charge on the oxygen and partial positive charges on the hydrogens. It won't be +1 or +1 and -1 or -2. It'll be maybe +0.3 and -0.3, something like that. In these cases like this, it's really hard to determine what the charge will really be in covalently bonded compounds. So what we've done is we've decided to use these things that we call oxidation states, which are essentially hypothetical charges that we put on the atoms in a covalent compound, which are basically the charges that the atom would have if the compound were ionic. It's not, so these charges are not real, but they're useful for bookkeeping purposes just to keep track of where the electrons are. So the overall number of electrons in the molecule will be the same either way, whether you figure out the real partial charges or whether you just use these hypothetical oxidation states. But it's easier to use the oxidation states because the oxidation states are whole numbers. And you can get them by just assuming that the compound is ionizing, even though it really isn't. Okay, so it's basically assumes a total transfer of electrons when they're actually being shared, albeit unequally. And calculation of partial charges is really complicated. So we don't want to have to do that. So when assigning oxidation states in the atoms in a compound, normally what we want to know is the oxidation state of each atom of each element in a compound or polyatomic ion. And we want to know the charge or the oxidation state of each atom of each element so that we can compare on an equal basis from reactants to products. Because the atoms rearrange themselves and you come out with products that have different formulas from the reactants, if you just find out the overall charge on a certain element in a reactant versus a product, you may end up with different numbers of atoms of that element in the reactant versus the product, which can make it look like the charge changed, even though it didn't. So we're looking at the charge on each individual atom of each element in the reactants and the products. So for assigning oxidation states or numbers, when looking at oxidation reduction reactions. First of all, the first rule is that the oxidation state of each atom in a free element, that is an element that's not bonded to anything else, is 0. So for example, if you've got sodium solid, that would be sodium atoms, and the charge is 0. And you can actually write it in as 0 if you want to when dealing with oxidation reduction reactions. If you have Cl2 gas, that's the way chlorine normally comes, and so Cl2 gas is the free element, and so that would have 0 charge. And as I stated back in chapter 1, sulfur often comes in clusters of 8 atoms, and so S8, as long as it's not bonded to any other element, would be the element sulfur, and that would have 0 charge. Okay, so that's pretty simple. Number 2, the oxidation state of monatomic ions would just be the charge on the ion. So if you have a +1 sodium plus ion, the oxidation state would be +1, which is, the book wants to write that as +1. I tend to write it as 1+, and it doesn't really matter to me which way you want to do it. If you have a chloride ion with a Cl minus, then the charge or the oxidation state would be -1 or 1-. If you have a nitride ion, it would be written as N3-. The oxidation state would be -3 or 3-. Okay, simple enough. The oxidation state of common nonmetals, there are some parts here because the nonmetals are where it gets a little hairy, because the nonmetals can combine with each other in so many different combinations. You've got hydrogen, which will always be +1 with nonmetals, but will always be -1 with metals. Okay, those are the hydride compounds. Oxygen is always -2 unless it's bonded to fluorine, in which case it will be something else, or in peroxide type compounds when oxygen will be -1, or in compounds that are known as superoxides, which are really unusual, in which case the oxygen will be -1/2 or -0.5. For the halogens, that is group 7A, fluorine is always -1, no exceptions. That's like one of the few things where there's no exception. Fluorine is always, always, always -1. The other elements in the halogen series will, chlorine, bromine, iodine, will be -1 unless they're combined with oxygen or one of the halogens above them in that group. Then they will be something else. And you're going to have to figure out what that something else is based on the overall charge and what the charge on the chlorine, bromine, or iodine need to be in order to make the overall charge work out. We'll see some examples actually in the next lecture of that. And number 4 is the total or the sum of the oxidation states of all of the atoms in a molecule have to equal 0. Because there's no overall charge on a molecule by definition. So for instance, if you're talking H2O, the overall charge on H2O has to be 0. So I've written a little 0 after it. The overall charge on something like CO2 has to be 0. If you're talking about a polyatomic ion, though, the sum of all of the oxidation states of all of the atoms in a polyatomic ion have to total up to the charge on the ion. So for example, if you're talking about the carbonate ion, that got a little smudged, but if you're talking about the carbonate ion, CO3, the total of all of the oxidation states of the carbon and the 3 oxygens has to add up to -2. And if you're talking about the nitrate ion, then the oxidation state on the nitrogen and the 3 oxygens have to total up to -1. Okay? So those are the rules as presented in the book. I have some rules that are presented in other books, and I'm not sure why this book doesn't mention them, that may actually make it easier for you to figure out what's going on and to figure out the charges on nonmetals that are involved in compounds. But we've run out of time for this segment, so I'm going to have to let that wait until next time. So next time we will pick up with electronegativity, and what I think anyway is an easier way for determining oxidation states among nonmetals in compounds. Okay, so I'll see you then.